Hello students. This lesson is on the law of cosines, which will be a tool to help us solve non-right triangles, and is a follow-up on the lesson on the law of sines. Now given any triangle, the triangle in this image appears to be acute, but this is a general drawing, so it could also represent obtuse triangles. If you take any one side and square it, such as a squared, it will be equal to the sum of the squares of the other two sides minus 2 times the product of the other two sides times the cosine of the angle opposite A. So that will be angle alpha. I will consistently have alpha be the angle opposite the side A, beta be the angle opposite the side B, and theta be opposite the side C. This formula, which we will not prove, is known as the law of cosines. This equation can be written in 3 different ways, depending on which side you're starting with. So for example, b squared is equal to the sum of the squares of the other two sides, a squared plus c squared, minus twice their product times the cosine of the angle opposite b, which is beta. Or we can say that c squared is equal to the sum of the squares of the other two sides, a squared plus b squared, minus twice their product, 2ab, times the cosine of the angle opposite c, which is theta. Each of these 3 equations can be rewritten solving for the cosine of the angle. For example, let's take the first one. I will add this part of the equation to the other side and subtract this part of the equation to the right side. Now I can divide both sides by 2bc. So here's one variation of the law of cosines where the cosine expression is isolated, and I could do it for any of the 3 equations up here, giving me the following collection of 3 variants. Cosine of beta can be found by doing a squared plus c squared minus b squared all over 2ac. And the third equation can be solved for cosine theta, giving a squared plus b squared minus c squared all over 2ab. All of these equations collectively are known as the law of cosines, which, together with the law of sines from our last lesson, can be used to solve every solvable non-right triangle. In that lesson, we used the law of sines for solving SAA and SSA triangles. An SAA triangle stands for side angle angle, and it's when we knew any one side, doesn't matter which one, and any 2 angles. So side B with these 2 angles, side B with these 2 angles, or side B with these 2 angles, or any other side with any other pairing of angles. And in SSA, side-side angle was when we knew 2 sides and then an angle that's not an angle between them. So if I know A and B, I can also know beta or alpha. Now related to SSA are SAS triangles. This is when you know 2 sides and the angle between them. So wrapping around in order, we would have a side and then an angle and then a side. We discuss SAS triangles on the next page. The solvability of SAS triangles. Like stated above, an SAS side angle side triangle is one where any 2 sides and the angle between those 2 sides are given. The triangle below is not drawn to scale. Determine whether it is solvable. If so, solve it, and classify the triangle as acute or obtuse. Specifically, find the angle alpha using both the law of sines and the law of cosines. So first of all, why is this an SAS triangle? It's because we know 2 sides and we know the angle between them. So wrapping around, we know a side, an angle, and then another side. Let's label all these angles and sides. Alpha is already labeled for us, so opposite it we will say is A. We'll say that this 40 degrees is beta, so opposite it will be side B. Therefore, the 6 feet must be side C, and opposite it will be angle theta. Now, the law of sines will not be useful here, because notice I don't know any side opposite angle pairings in their entirety. Beta and B have one unknown, which is B. Alpha and A have one unknown, alpha. And C and theta pairing have one unknown, which is theta in this case. So the law of sines is not a useful tool for solving this particular triangle. This is where we will need to use the law of cosines. Let's use it first to find the missing side. So I'm going to grab the version of the law of cosines that has b squared isolated, and then begin substituting. We don't know b, so we have b squared is equal to. We do know a is 10, so 10 squared would be 100. We know c, which is 6, so c squared is 36. And then we do 2 times a times c, so 2 times 10 times 6. That'll produce 120, and then times the cosine of beta, which is known, 40 degrees. So b will be equal to the square root, keep only the positive because b is a length, of 100 plus 36 is 136, and then minus 120 cosine of 40 degrees. So type this into a calculator, make sure you are in degree mode, and we get a result of about 6.64. And this would be measured in feet. Let's find theta first. I'm going to grab the version of the law of cosines that has the cosine theta already isolated, and then begin substituting. Cosine of theta will be equal to a squared, which is 100, plus b squared. B squared is this expression right here, which, when simplified, became this radicand. And then minus c squared, which is minus 36, all over 2 times a times b, where b is the square root of 136 minus 120 cosine 40 degrees. Therefore, theta is going to be the arc cosine of this expression, which I will simplify a little bit. 100 plus 136 minus 36 will be 200, and then minus 120 cosine of 40 degrees, divided by 2 times 10 is 20, times the square root of 136 minus 120 cosine 40 degrees. And now we reach for a calculator. Now we can continue to store values as variables. For example, I can say that a is 10 and c is 6. And then theta, so you could type in theta to make the theta symbol, or more easily, you can use a different letter to represent theta, such as capital T, or sometimes people use capital letters to stand for the opposite angles. So an uppercase C can stand for the angle opposite C, which is our theta. And type in arc cosine of, and now the convenient thing here is I can just type in the formula because a, b, and c are all stored as values. So it was a squared plus b squared minus c squared, lowercase c, and then all over 2ab. Make sure that you are in degree mode, and so our answer is about 35.52 degrees. Now once you know theta, we can find alpha by knowing that the sum of the interior angles must be 180 degrees. So we're actually going to find alpha 3 ways. Alpha will be 180 degrees minus beta minus theta. And beta and theta are now known. Using technology, let's insert a line for beta, which was 40 degrees. I'll use capital B for the beta, or you could type in the word beta, and it was 40 degrees. And now alpha, you can type in alpha, or I'll use a capital A for the alpha, is equal to 180 minus beta, which is capital B, minus theta, which is capital C. And so we get the angle alpha is about 104.48 degrees. So right away, because I have an obtuse angle, I know that this was an obtuse triangle. And we've completed our task by solving this triangle. But as instructed, let's also find the angle alpha using the law of sines and the law of cosines. Let's do the law of cosines first. I'll grab the version of the law of cosines that has the cosine alpha isolated. Solving for alpha, we get alpha is equal to the arc cosine of this fraction. And then reaching for technology, let's find alpha again. This time I'll call it a sub 2 and just compare it to what I got for a moment ago. Arc cosine of b squared plus c squared minus a squared all over 2bc. And notice we get the same result, 104.48 degrees. And now let's find alpha a third way using the law of sines. We know that sine alpha divided by a will be equal to, and I have some options here. Let's use the beta b ratio. So sine beta divided by b. Going to multiply this a to this side over here, and then do an arc sine. Let's call this capital A sub 3 for our third way of finding alpha. We do the arc sine of a times the sine of beta, and we're using capital B for beta, divided by b itself. Notice what it gives us, 75.52 degrees approximately. This is not the correct answer. This is because alpha is an obtuse angle. It's more than 90 degrees. The arc sine cannot return obtuse angles. It can only give you negative angles in the fourth quadrant or positive angles in the first quadrant. This does not mean that the law of sines is incorrect. It just means that when you isolate alpha by using an arc sine, that you may need to adjust your answer to be in the correct quadrant. So if I do the negative of this angle, that puts us into the fourth quadrant, and then add 180 degrees to this, will put us into a second quadrant position, and this is an angle in the second quadrant at which the sine has the same value as that other angle we just saw a moment ago that was in the first quadrant. So this is the angle we're looking for, and as you can see, it matches the other two. So the arc sine of this expression gave us a quadrant 1 answer, but alpha is an obtuse angle, or it needs to be obtuse. So we can actually find alpha by doing 180 degrees and then add the opposite of this arc sine expression. Or in other words, remove arc sine of A sine beta over B. And this gives us a quadrant 2, or in other words, obtuse angle. So one issue, if I had tried to find alpha first by using the law of sines right here, then I would not have necessarily known which of these two angles would be the angle I am looking for. And that is because given this information, keep in mind that this triangle is not drawn to scale, so it's not always easy to identify whether alpha needs to be obtuse or acute. In fact, the same thing is true for theta. So the law of sines to find angles has some cognitive challenges. However, using the law of cosines is free of this challenge. Any of these angles in here must be somewhere between 0 and 180 degrees. Using the law of cosines to find an angle, like we did right here, involved using an arc cosine. Well, the arc cosine function is a function that outputs angles that are in the first or second quadrants as appropriate. In other words, it'll give us acute or obtuse angles as appropriate. In other words, it will always produce the correct angle, and there is no ambiguity, unlike using the law of sines, where I had conceivably two different angles and I had to choose which one was appropriate. So the lesson moving forward is that the best way to find a missing angle between the choices of using the law of sines or the law of cosines, always use the law of cosines. It will give you the correct angle, whether it be acute or obtuse. Now, how did I know that this triangle was solvable in the first place? We were given a side, and the angle in between them. Well, it turns out that if you know two sides and the angle between them, as long as that angle, of course, is between 0 and 180 degrees, exclusive of the endpoints, so strictly between 0 and 180 degrees, then the triangle will always be solvable. If you know one side, it doesn't matter how long it is, and you know another side, it doesn't matter how long it is, and then you vary the angle between these sides, it doesn't really matter how long these sides were, nor does it matter what that angle is. If I pause this and use any length I want, I can always complete a triangle. So SAS triangles are always solvable as long as the two sides have length and as long as the angle between them is somewhere between 0 and 180 degrees exclusive of both endpoints. Okay, let's go to the next page. The solvability of SSS triangles. Now, an SSS, or side-side-side triangle, is one where just the three sides are given, so no interior angles are known. Now, triangles cannot have any side lengths that they want and still be possible. Recall that the sum of any two sides must always exceed the length of the third side. So all three of these inequalities must be true. So 7 plus 9 is 16, that's more than 3, check. 3 plus 7 is 10, that's more than 9, check. And 9 plus 3 is 12, that's more than 7, check. So this is a possible triangle, and all that we need to do now is find the interior angles. Now, this triangle is not necessarily drawn to scale, so I don't know if the result should be an acute or an obtuse triangle. But let's call this side here on the left A, so alpha will be its opposite angle. Let's say 9 is the length B, so beta is its opposite angle, and then we'll say this 7 inches is the length C, so theta is its opposite angle. It won't matter which angle we find first. Let's find alpha. So I'm going to grab the law of cosines formula that has the cosine of alpha isolated. Therefore, alpha is the arc cosine of this expression. All of these side lengths are whole numbers, so it'll be easy to do some work here by hand. B squared is 81, C squared is 49, A squared is 9, all over 2 times 9 times 7. This will be the arc cosine of 121 over 126, which is about 16.20 degrees. Make sure your calculator is in degree mode. I will continue using the law of cosines until I have all but one of the angles. Doesn't matter which one we aim for next. Let's go for beta. So here's the version of the law of cosines where cosine beta is isolated. Therefore, beta is the arc cosine of A squared is 9, C squared is 49, B squared is 81, all over 2 times 3 times 7. This is the arc cosine of negative 23/42. Notice our argument is negative this time. When you do the arc cosine of a negative number, you will get a second quadrant angle. So this is how I know beta is going to be an obtuse angle. And we get about 123.20 degrees, giving us an obtuse triangle. And now that we know alpha and beta, we can find theta by doing 180 degrees minus alpha minus beta, which is about 40.60 degrees. And we have solved our triangle. There's no ambiguity here. I know these are the correct angles because the arc cosine will give me acute or obtuse angles as appropriate every time. Let's look at this next triangle. Let's first determine if it's possible. Notice that 2 plus 3 is 5, and that does not exceed 6. So despite the fact that I drew a triangle and labeled these sides measurements are not possible. In reality, 2 and 3 are too short. And if you rotated them down so that they laid flat, you can see they don't even touch because 2 and 3 only cover 5 of the 6 meters. So there's no way that they could meet. So 2 plus 3 equals 5, and that's not more than 6. So this second triangle is not possible. Okay, let's go to the next slide. Solvability of AAA triangles. Now, an AAA, or angle, angle, angle triangle, is one where just the 3 angles are given and none of the sides. Now, the triangles below are not drawn to scale. Determine whether each triangle is solvable. If so, solve it and classify the triangle as acute or obtuse. Let's call the 40 degrees alpha, the 60 degrees beta, and the 80 degrees theta. Now, recall that for any triangle, the sum of the interior angles must be 180 degrees. And in this case, 80 plus 40 plus 60 is 180. So this checks out, and this is a possible triangle. However, its solution is not unique. I could imagine a small triangle with these same angle measurements, or imagine scaling it up to a larger triangle, but with the same angle measurements. So it is solvable, but there are infinitely many possible triangles. In order to get a unique solution, we would need to know at least one of the side lengths. So if one side is given, a unique solution can be found. For example, let's assume that A is 10 meters. Then the other sides would be B and C. And I would just use the law of sines to finish this out. So I'll use the alpha A pairing with a theta C pairing to help me find C. So we would know that C divided by the sine of theta, which is 80 degrees, would be equal to A, which is 10 meters, divided by the sine of alpha, which is the sine of 40 degrees. So C would be 10 sine 80 degrees over sine 40 degrees, which I won't compute. And we could find B similarly. B divided by the sine of beta, where beta is 60 degrees, would be equal to A, which is 10, over the sine of alpha, which is sine 40 degrees. So B would be 10 sine 60 degrees over sine 40 degrees. Of course, I had to know A in order to do any of this. In other words, I had to know at least one side. Now look at this next triangle. In this case, alpha plus beta plus theta is equal to 170 degrees, not 180 degrees. So this triangle is not possible, or not solvable. Okay, let's go to the next page. Find the angle alpha in the image below. So we have a triangle here drawn in the xy plane. One vertex is labeled at 3, 3, suggesting that the origin is right here. So we have an x and y axis. So this point must be 1, negative 1. And this point over here, the other vertex of the triangle, must be at negative 3, 2. I don't need to solve the entire triangle, just to get enough information so I can find out what alpha is. So the side opposite alpha we'll call A, and the other two sides B and C. Now I can actually find A, B, and C using Pythagorean theorems. Notice that A is the hypotenuse of this orange right triangle, where the legs are easy to count out. So I know that A squared must be equal to 2 squared plus 4 squared, just using the Pythagorean theorem for right triangles. So A must be the square root of 20, which you could write as the square root of 4 times the square root of 5, or in other words, 2 root 5. The units here are not specified, so I'll just say units. B and C can be found similarly. B is the hypotenuse of this red right triangle, whose side lengths are 1 and 6. So B squared is equal to 1 squared plus 6 squared, telling us that B is the square root of 37. And C is the hypotenuse of this green right triangle, and the legs are 3 and 4. So C squared must be equal to 3 squared plus 4 squared, giving that C is the square root of 25, or 5 units. Now my goal here is just to find alpha. So I'm going to use the version of the law of cosines where cosine of alpha has been isolated. Therefore, alpha is the arc cosine of B squared is 37, C squared is 25, and then minus A squared is 20. Easy to square all of these radicals here. Just remove the radical. Divided by 2 times B, which is radical 37, times C, which is 5. This gives us arc cosine of 42 over 10 rad 37. Notice this argument is positive, so the arc cosine should give me an acute angle. And we get about 46.33 degrees. All right, the next page. On this page, we provide a summary of solving non-right triangles. This includes summarizing ideas from both this lesson on the law of cosines and the previous lesson on the law of sines. And this encompasses all types of triangles where 3 bits of information are given about the triangle. In this first case, no side is known, so we just know the 3 angles. Then we have a case where only one side is known and 2 angles, specifically any one side and any 2 angles. It doesn't matter how they're positioned relative to each other. Then we had 2 distinct cases where 2 sides were known and then 1 angle. And this we did have to break up into 2 subcases. This first subcase is where you know 2 sides and an angle opposite one of those sides. In other words, not the angle that's between the 2 sides. And then this second subcase is where you know 2 sides and the angle between. We're calling that the SAS. And then finally we have a case where 3 sides are known. Let's go to the first case here. No sides are known, but 3 angles are known. Comments on solvability. We know it's solvable if the interior angles add to 180 and not so otherwise. And if no sides are given, then there's really infinitely many solutions. And there will only be a unique solution if one side is also known. But given a side, use the law of sines to find the other 2 sides. Now, if you know any 2 angles and any one side, we addressed this in the last topic on the law of sines, and they are always solvable as long as the 2 angles add to less than 180 degrees. That gives you room to find the third angle. And that third angle is found by doing 180 degrees minus the sum of the other 2 angles. And now we know all the angles, and we know a side, so we can use the law of sines to find the other 2 sides. Now, SSA, 2 sides and an angle not between them. So let's say we have this situation where we know A, B, and alpha. If A was somewhere between 0 and B sine alpha, excluding B sine alpha, then we had no triangle. If A was equal to B sine alpha, then we had one right triangle. If A was somewhere between B sine alpha and B, excluding the endpoints, then 2 triangles were possible. And if A was B or more, 1 triangle was possible. This was all discussed in the last topic on the law of sines. If the triangle is solvable, we can find beta using the law of sines. And sometimes we get more than one answer for beta, an acute or an obtuse angle, when we are in this case here. Then you can find the third angle theta by removing alpha and beta from 180 degrees. And then you can find the last side, C, also using the law of sines. Now, in the SAS case, where we know 2 sides and the angle between them, so let's say we know A, B, and theta, this was always solvable if that given angle theta was somewhere between 0 and 180 degrees, excluding the endpoints. And I would recommend finding C using the law of cosines, then alpha using the law of cosines, and then the final angle, beta, can be found by doing 180 degrees minus alpha minus the given theta. And then 3 sides. This one is also always solvable if the sum of any 2 sides always is more than the third side. So A plus B has to be more than C, A plus C has to be more than B, and B plus C has to be more than A. Then you can find any 2 angles, I'll say alpha and beta, using the law of cosines for each one, and then once you know 2 of them, you can find the third by doing 180 degrees minus the 2 that you found. All right, this summary concludes not only this lesson on the law of cosines, but also is a recap on the previous lesson on the law of sines.